Well, thank you. Today I'd like to talk about large-scale, robust online matching. Okay. Now, for e-commerce, the ultimate goal is essentially to effectively connect users with products or sellers. So therefore, the core of any e-commerce platform essentially is the efficiency. Now, in order to improve the efficiency of connecting the user with product seller, there are two major issues need to be addressed. The very first issue is the prediction. You need to be able to forecast what exactly the user needs at any moment. The second issue is matching. So based on your forecasting of users' need, you need to come up with appropriate matching of the user's need with the product you have in stock. Now, for prediction problem, Alibaba have done very extensive work. Usually, it's going to divide into several steps. The very first step is to integrate all the information that you have, including the transaction information, the behavior information of user online and offline, and also include the local basis service information to build a comprehensive user profile. Now, then you're going to take this user profile together with the online user feedback, as long as the contact information you have, to fit all this information into a very powerful learning machine that often includes logistic regression, tree-based approach, as well as deep learning method, essentially to come up with accurate prediction about what user would like to see and would like to purchase at any moment. Okay, now if we come to the matching question, usually they're looking at the two different cases. The very first case is what I call the easy case, meaning in this case, you do actually have abundant supply that can meet with whatever users demand. Okay, so in this case, the supply is much larger than the demand. So in this case, you can simply just present the user with the best predict items without any worry. Now, when we come to the second case, it is much more challenging. In this case, turns out the supply is much more limited, may not be able to provide what exactly user want based on prediction. Okay? This is where the matching algorithm, the matching problem comes into playing the role. And that's the thing of the talk. Okay, so let me first of all briefly describe in abstract sense what I mean by assignment problem or matching problem. So typically speaking, a matching problem is going to describe as a bipartite graph. Okay, on one side of the graph, you see a list of agents. On the other side of the graph, you see a number of tasks. So whenever you assign a particular agent to perform a task, you're going to receive a reward. Okay? So the ultimate goal of assignment problem is to maximize overall reward. Now, if there's no constraint whatsoever, then the assignment will be straightforward. You simply assign each user to the task with the largest rewards. But unfortunately, that's not the case in reality. Often it's the case, in reality, you're going to encounter with constraints. The constraint usually limits the number of tasks that can be performed by individual user or the number of agents that allow to perform on each individual task. So therefore, the challenge optimization problem you encounter is to find out the best assignment under those constraints. And this is the discussion we're going to have here. Let me give you a few examples just to illustrate how this problem can be applied and to the e-commerce. I give the few instances here to illustrate the application in Alibaba. So the very first application is online display advertisement. So in this case, for each user, for each opportunity, you're going to present the user with a particular advertisement that hopefully will fit in with his or her interest. Okay? So therefore, the overall award you're going to receive is the number of clicks. You like to maximize the overall number of clicks that you can receive. Now, in this particular assignment instance, the constraint that you encounter coming from the budget of individual advertiser. Now, given the fact that each advertiser have limited budget, therefore the number of impressions that you allow to display individual advertisement is going to be very limited. So therefore the question is, how can you maximize your revenue or maximize the number of clicks under the constraint that each advertiser has a limited budget and will give a limited number of impressions. Now the second instance of the application of assignment problem is what I call the Ask All project. I thought it's very interesting project that deserves a good discussion here. So the problem we look at here is following. Now for most of the users, before they make the final decision about the making purchase, he often have a slight doubt about the product of the items, right? And he really wants someone can clear out the doubts before he make the final decision. This is a particular case if the price of the item is very high, okay? Now in Alibaba, we create a product called Ask All. The idea is follows. Basically, all the users, whenever you have a doubt, you actually can type your question in Alibaba platform. And the system would actually look at the user who have used that product before and will identify the subset of those users who are willing to answer or address those questions for those doubts. Okay, so as you can see in this case, the agents becomes the users who can answer the question, and the task are those questions being raised. So our goal is to maximize the overall number of questions that can be addressed. Now the constraint here is essentially each time if you ask a particular user a question, you really should be concerned about the user experience, because whenever you ask user too many questions, that created too much disturbance and will result in no user being willing to answer any question at all. So by limited number of questions that can be asked, that actually causing a challenge assignment problem here. So this is the example of the Ask All project. I know most people don't really read Chinese, but first highlight box is essentially the question being typed in by a particular user, and then within the second box, you actually see the answers that are being solicited from subset users that we have identified for answering. Okay. Now there are many other instances of application of assignment problem. Due to the time constraint, I'm not going to elaborate with more details. Okay, and so unfortunately, I know this is a really not wise action by presenting with equation, but really to make my point clear, I thought this is absolutely necessary. So bear with me, and I hope that this is not causing too much trouble for the audience here. Here we have n different number of agents, and we have m different number of tasks. Now, whenever you assign agent I to the task J, you're going to receive a word Cij. And you also have a constraint Ki, which is limited number of tasks can be performed by a particular agent. So for the equation that people see on the screen, we have a decision variable called Xij. This decision variable decides who is going to perform which task. So if Xij is 1, meaning the agent I is assigned to perform task J, otherwise Xij should be 0. So the object function list in optimization problem is essentially the summation of overall awards. That implies our goal is to maximize overall awards. And you also see two constraints below the objective function, which illustrates that limited number of tasks can be performed, or limited number of agents allowed to perform for each individual task. Okay. Now notice that in the left equation you have to deal with a binary variable. For people familiar with the optimization problem, you know this is non-convex, most likely to be NP hard. Therefore, typical strategies relax them to a continuous variable. So it was listed on the right side of the screen. Typically speaking, you have the round-up procedure allows you to take the fraction number into a binary one. Now, in general, this assignment problem has been very well studied in the research community, and it has a history of at least 50 years. But there are two important issues, unfortunately, would never be seriously addressed by those researchers, which unfortunately have a major impact in practice. The very first issue is about the quantity. So as you have seen, that turns out that the results of the solution depends on CIJ, the award. And most of the cases, those awards are actually estimated from the historical data. And as the result, those estimations can be inaccurate, sometimes can be very off target. So the very first question we're going to address is how could you come up with a proper assignment even when those awards are inaccurate? The second issue is that for most assignment problems, we assume that you know all the tasks beforehand, such that you can do an entire planning for everything. But again, that's not the case. In many cases, like Ask All project, turns out the task or the questions are emerging in online fashion. Therefore, there's just no way you can do the batch planning at all. So the second question is, how are you going to deal with the emergent task in online fashion? And that leads to the key technology I would like to briefly describe over here. One is about the robust matching, the other one is about the online matching. Okay, so for the robust matching, I'm going to look at the two different technologies. One is called the robust optimization, very well established technology in the OR community. And second is what I'm looking at, the stable matching technique, which interestingly are the well-established theory in the economy community. So let me first look at the robust optimization approach. So in many cases, even though you do not have accurate estimation about the word, most of the cases you actually can come up with interval that tells you that even though you cannot get you cannot exactly pin down the value of CIJ, but you actually know the range of CIJ that can fall into. So if that information can be taken into account, then our results will be much more robust compared to the fact just taking a single guessed value for CIJ, right? So therefore, the optimization problem we face over here is to find out assignment that can perform well regardless which value of CIJ you take from that interval. And that turns out to be the exact spirit of robust optimization, and usually by taking the uncertainty into account, you actually end up with what we call minimax or convex concave optimization problem that usually can be solved by a Nesterov method. Okay? So we actually apply this technology to the online display advertisement. Basically, we're running against 10,000 different advertisers. We have over 100 million users. In experiments, we find out by taking into account the uncertainty of those awards, you actually can dramatically improve your revenue in advertisement, in this case by 20%. Let me look at the second technology. It's called a stable matching. As I said, this is actually fundamental theory developed in the economy community. Turns out the guy who developed the theory, Professor Evan Ross from Stanford University, won the Nobel Prize in 2020 because of this theory. Okay, now to illustrate the idea of stable matching, let's start with the marriage, because marriage is very typical matching problem, right? So consider you have a pool of men and you have a pool of women. Now for each man and for each woman, you ask them to come up with a list of preference. So look at the example we have on the screen. We have 3 men and 3 women. Each of the men and women have come up with a preference of their partner. So for instance, if we look at the M1, the first man, he liked the women W2 most, and then W1 second, and probably the W3 is his the last choice. Okay? So given this preference from men and women, the questions, what would be the best, what would be the good matching between men and women? How are we going to form the couple based on their preference? Okay? So in order to illustrate what I called good marriage, let's consider instance of matching, okay? So let's consider simple matching. I simply married M1 with W1, M2 with W2, and M3 with W3. Okay, now let's see what's the problem with this simple instance of matching. Turns out this is a bad matching. This is a very unstable matching. Why? Because if I pick up a pair, M1, W2, this is not married couple, right? Now, if you're looking at the preference of M1, you realize that actually M1 prefers W2 than W1. And remember that the W1 is the married partner for M1. So in this case, if M1 meets with W2, he actually has a tendency to divorce his current partner and try to marry with W2. Now, if you look at the W2, you find exactly the same situation because W2 in her preference turns out M1 is more preferred than M2, which is her current partner. So again, W2 has a tendency to divorce her current partner and to form the couple with M1. So in other words, in this particular assignment, if for some reason M1 and W2 meet, they actually both have a tendency to divorce the current partner and form a couple. And that causing a very unstable results, and that is a bad matching results. Okay? So therefore, a good matching has to be a stable matching. A good matching has to be the case that you do not find those blocking pair. And that's the essential idea behind all stable matching theory. But the question is, how am I going to find out such a stable matching? Is there any way I can find out efficiently? The answer is yes. Arison was invented 50 years ago. It's called the deferred acceptance algorithms. He actually can find not only a stable matching, he actually can find the best stable matching among all the possibilities. Okay? Okay, now the question. Okay, so the question is, why this have anything to do with our matching? Now remember that in this matching algorithm, we actually only need partial preference of each individual user and the task. And therefore, we do not need any exactly numerical value for those awards at all. And that allowed us to make this algorithm to be much more robust to any errors that happens in those estimations. Besides this robustness advantage, it also being more efficient compared with standard linear programming problem. Also, it has very strong optionality guarantee. I'm not going to elaborate them with more details. Okay? So we're actually running this idea against the task called the mobile message pushing. So basically, we have 400 different messages are coming every day. We like to push the message to different users. Our goal is try to maximize the number of opening by individual users. So the user participating in this experiment is over 10 billion users. So we find out if we're running these algorithms against this particular task, a mobile message pushing task, we actually would be able to improve our opening rate by 20% compared to the robust optimization approach we have been listed before. So again, this is very, very powerful tool given its advantage in terms of only required partial preference, in terms of its highly efficient compared with typical linear programming problem. Okay? So now let me come to the second part of this talk, which is online. So as I said before, one limitation of the assignment problem is that it requires to know all the tasks beforehand, but that is not going to be the reality, right? So problem like ASCII, you actually only know, you'll never be able to predict those questions beforehand. So therefore, there's no way you can run your assignment algorithm against those questions. Okay? So the simple approach to deal with this online question is simply for each of emerging the task you receive, you look at all the candidates of users that could be able to answer those questions, and you find the one that who actually going to provide the best answer beforehand, right? So this is usually called the greedy algorithm. But unfortunately, this greedy algorithm is not going to work well in reality. Let me show you a simple example just to demonstrate the fundamental flaw of this greedy approach. So consider you only have two questions, Q1 and Q2, and you have two users, user A and user B. Now, if you look at the user A, it actually have 80% chance to address both questions based on estimation. Now, if I'm looking at the user B, turns out user B only have 79% chance to answer the first question, but it only have 10% chance to answer the second question, okay? Now, imagine that if the question 1 came in the first place. Now, if we compete between the user A and the user B, apparently user B is going to be user A is going to be the winner because it has a slightly higher chance to answer the question right. Now, let's further assume that due to the user experience, we only ask each user one question. So whenever we ask the user A for the question 1, then we simply eliminate the user A for the rest of the questions. Now, when the second question comes in, the user A has been eliminated from the candidates. Now, you can only resort to the user B for the question answering, but unfortunately, based on estimation, user B only have a 10% chance to answer the question right. So as you can see, if we actually did a slightly wise decision, probably we are not going to run into such awkward situation if you can let user B to answer the first question and then user A answer the second one. So the question is, unfortunately, we have no idea what question is going to come on in the pipeline, so how are we going to address such fundamental flaw? So it turns out there's a very nice theory from the online algorithm called the prime dual theory. Basically, the key idea is the follows. That is, whenever you ask a potential agent to perform a task, you always want to discount his award for the following task he can perform. Okay? So this is called the discount award. And using the discount award, you actually select the user, not based on the original word, to address the task. Instead, you're using the discount award as a basis to decide who is going to perform which task. And that becomes the key recipe to save the problem we have encountered before. So actually, you can prove a strong theory to tell that even though we do this assignment in online fashion, meaning that I have no idea what is going to happen in the future, but you still can actually do a pretty good job compared with the situation that if you know all the tasks beforehand. So due to time constraint, I'm not going to elaborate with more detail about the guarantee. So we're actually running this approach against AskCall. So in this case, we roughly have 500,000 questions being raised by different users on a daily basis, and we have a pool of 20 million users that are waiting to address the questions. Now, if we run this online algorithm based on this kind of word theory, compared to the greedy algorithm, we find that the answering rate can be improved by roughly 40%. Very, very significant improvement in terms of the user answering. Okay, now, so one of the limitations with respect to the online algorithm is that one is this algorithm can only address so-called linear words. Second is that those algorithms, even though have some guarantee, but in terms of regret, the guarantee is very vague. So we're addressing this question by coming up with online constraint optimization with long-term constraints that try to make it to be more general framework. Again, this is due to the time constraint. I'm not going to jump into the technical detail, but we do actually running this online constraint optimization approach against what we call the constrained traffic optimization problems. That turns out to give us a tremendous boost in terms of CTR. We find if we running this approach against the greedy, we turns out can improve our CTR by almost 100%. Okay? Okay, so I'm going to end up with my talk with a slightly different subject. So everybody has been knowing that artificial intelligence has been a very, very popular topic in the recent days, right? Because we see a tremendous success of applying the deep learning to speech recognition, to natural language processing, to image processing, image understanding, et cetera, et cetera. Also see the great success of AlphaGo. Okay, but in my opinion, all these efforts actually have one strong limitation. That is, essentially, all these efforts are restricted their folks to extract the best bit of capacity out of machine. Now, for a platform like Alibaba, we not only have tremendous amount of data accumulated over years, we also have the computational power, but more important, we have 500 million people behind that platform. So the question is, can we fully leverage not only the data, not only the computational power, but also the intelligence of these 500 million people behind the platform to create one single integrated intelligent platform? Right? So just imagine, for instance, consider if someone asked a question to a question answering machine, say, who's going to be the next UN Secretary General? Right? Now, apparently you can do this by crunching up your QA machinery like many people did. But often it's the case that due to the limitation of knowledge or limitation of data, you may not be able to answer the question right. Now, if actually instead of trying to answer the question from the machine, I can also looking at the people behind the machine, right? So I can actually using my matching algorithm to identify the subset of user who actually may have reasonable knowledge to answer that question. Right? And then I'm going to forward that question directly to the right user who are likely to address the problem. Okay? So in this case, if I be able to identify the right users, then I would be able to actually address the answer directly without having to crunch my machine. But from the viewpoint of the user, they really don't see much of difference because either the answer coming out of machine, out of the data, or the answer coming out of the 500 million people behind the machine, nobody cares. What really cares from the viewpoint of the user is give me the right answer. And I think by integrate the intelligence machine, and by integrate the intelligence machine with 500 million people, that will make even powerful platform to make even more intelligent the system. Okay, so that's be the part of my talk. Thank you very much.